In this video, let's talk about the frameworks in which one can do physics, right? So from the title itself, it gives you an idea that there are actually a set of frameworks from which one chooses and then they do physics in that particular framework, right? So first of all, one has to know what a framework really means, right? So a very casual definition of a framework. Well, it goes something like this, that a framework is kind of a basic structure that underlies a particular system, right? So one of the very important note or point over here is that by themselves, they do not constitute any kind of theories, right? So a framework does not constitute any theory. But for one to have a theory, we need some things, right? So what do you need? Well, on one side you have framework or a set of frameworks, and on the other side you have something that is called a degree of freedom or degrees of freedom, right? And their interactions, right? So when you have both of these, when you combine these two, what you get is a theory, right? Okay. And again, important point is that you combine framework and degrees of freedom and their interactions to get a theory. So to explain this, we can use something that may be called a correspondence principle, right? And well, we are going to start with a frameworks now, and we're going to start with a very say a basic one, and the one that almost everyone, especially all of those who do physics, they know about. It's called Newtonian Mechanics, and it is a very basic framework because we all know about it. We study Newtonian Mechanics in the first semester of our undergrad, or even in a high school and college, right? Well, it is a very basic one, so I'm going to label it with NM, Newtonian Mechanics, and you solve this equation, that is F equals the time derivative of momentum, right? And you solve this equation for a system to understand or to figure out how the system evolves or the dynamics of a system, right? Well, the Newtonian idea is something like that you have a complete separation of space and time. So they are not together. Space is something else and time is something else. And there is a concept of absoluteness. Absoluteness, yeah, I hope I pronounced that right. Well, the absoluteness of time. And we'll see that this absoluteness of time is violated in special relativity, right? Well, Newtonian mechanics is actually what we teach students that are in, say, their first semester of undergrad, and then we make them think that not only that this is the hardest thing that they're ever going to do in their lives, but it's actually also true, right? And then we spend the rest of their degree, especially in General Relativity course, we teach them that it is in fact wrong, or kind of wrong, right? It's actually incomplete. So the Newtonian idea is actually incomplete. Well, let's make a diagram, or whatever you want to call it. I'm going to label Newtonian mechanics as NM, right? Well, in Newtonian mechanics, we talk about particles and fields. So both of these things, right? And it is pretty much obvious that Newtonian mechanics is the most limited framework, which we will see when we move along. And well, in Newtonian mechanics, we can still talk about relativity, and that concept is called it's called Galilean relativity, And you all know about it, I hope, but if you don't, a very classic example would be that assume you're riding on a bus and the bus is moving at 60 miles an hour and you throw a ball inside the bus at 2 miles an hour. The observer that is outside the bus, he records the speed of the ball as 62 miles an hour. That is the addition or the sum of the two velocities, right? And that's Galilean relativity. Right. Well, now let's move on to something that's called special relativity. And I'm not going to call it special theory of relativity because, again, I said we're talking about frameworks, and frameworks are a bit different than a theory, right? As I have explained earlier. And so we have special relativity. So I'm going to call it SR, right? Now, we talked about correspondence principle, or at least I said that we can explain it or relate the frameworks with correspondence principle. And so there would be a correspondence principle, so for which one can go from SR to Newtonian mechanics. But in what case, right? The idea is if you have slow speeds, and when I say slow speeds, I'm comparing it with the speed of light. So if your velocity is much smaller than c, then you can get away with using Newtonian mechanics. Also, actually, some of the people think that Newtonian mechanics is easier to work with. I don't think so, but most of the people do, and I don't think so that they should, right? Well, again, in special relativity, we talk about particles and fields. Now, most of you all, when you go and tell people about special relativity, you might start with length contraction, time dilation, and that kind of stuff, right? Well, one of the very classic results of special relativity is the addition of velocity addition formula. And I believe that, you should start with that instead of talking about or impressing people with the idea of length contraction and time dilation. Well, the velocity addition goes something like this, that say you have a frame and this frame is not moving, but in this frame you have a particle that is moving with some velocity. Let's call that u, and say that this frame belongs to S, right? So I'm representing this frame with x and y axes. And now let's say that there is another frame, and this frame belongs to S prime. And S prime is moving with some velocity v, right? So the question is then, if you are S prime, then how would you, or what velocity would you observe for the particle that is moving with speed u in frame S, in a frame that belongs to S, right? And so, of course, then this is not a lecture on special relativity. So I'm just going to write down this formula. It's kind of pretty easy to derive as well. But the velocity addition formula is that S prime would record that velocity u prime as v plus u. So that's the sum of the velocity of the frame that's moving and the particle over 1 plus v times u over c squared. And then again, you don't have to remember these formulas, right? But of course you must know how to derive them. Well, and now one of the most beautiful thing about this formula is that when you work with very high speeds, right, your c is still constant, right? So the idea of special relativity is what? That you have a limit to your speed, and that is the maximum speed that one can go is the speed of light, or less than that, right? So this formula works out. For example, if we go back to the Galilean relativity, in that take an example that instead of a person throwing a ball in the bus, he takes a torch or something that emits photon, right, and he shines that. According to Galilean relativity, the velocity of that light should be, according to the observer who's outside, the sum of the velocity of the light itself and the velocity of the bus. But experiments show, and we all know now, that that's not true. Well, this Einstein's velocity addition formula takes care of that. Right. Okay. So I think that's all that I'm going to say about special relativity. And again, this special relativity is a framework. It's not a theory, right? Okay. So what do we have other than these two? There is a very famous one, and it's called quantum mechanics, right? So I'm going to write quantum mechanics over here by QM. So QM is for quantum mechanics, and we can also relate quantum mechanics or make a correspondence to Newtonian mechanics. And however, there are several ways of making this relation, right? So several ways from which you can get away with Newtonian mechanics instead of using quantum mechanics. One of which is, of course, you might think as if we have large systems or large if you have large systems, you can go and use Newtonian mechanics. You don't have to use quantum mechanics. But it turns out that for some of the large systems, you still need to use quantum mechanics, right? Well, first let me talk about what the Bohr's idea was. So Niels Bohr idea, he thought that quantum mechanics works for large systems. However, the spacing between the variables is very tiny. So you can take them as a continuous line, right? If the spacing is very small, so for example, if the spacing between these two lines is almost negligible, so they become one. And so then that is continuous. Discreteness vanishes. Right. Now, let me get rid of these funny lines. Let's talk about if you were, say, supposed to quantize a harmonic oscillator, right? So in quantum mechanics, the energy eigenvalues for that is it's n plus 1/2 h bar omega, right? But we also know this energy formula for a simple harmonic oscillator classically, and well, that is something like E equals 1/2 m omega squared times amplitude squared, right? So what one can do is then, say for example, you solve for a classical harmonic oscillator, right? And let's say that you have a mass of 1 kilogram, right? You have omega frequency as 1 hertz, right? And your amplitude is, let's say again, 1 meter. So we are talking about unit, right? So if we solve this classical formula with these what do you call them, variables, what you get is you will get, well, let's put it in there. So 1/2 times 1 times 1 times 1. You get 1/2, right? Okay, now what one can do is we can substitute this 1/2 in this equation for energy, and we can find out what n would be. And once we do that, we get n approximately equal to, it is to the order 23, right? 10 to the power 23. It's something like 4.7 into 10 to the power 23, right? Well, that's a pretty big number. Now, if you want to find the discreteness, what you do is you take delta E over E, and when you find this thing out, it's approximately equal to 0. And so what that means is that discreteness approaches 0. So discreteness vanishes, and so if discreteness vanishes, your system becomes continuous, right? That implies that your system is continuous. Well, there is also another way of interpreting this, and this was what I just told you was Bohr's idea or Bohr's interpretation. Statistically, we can have a statistical interpretation, and that is something like, say you have your classical behavior in fact rises due to the decoherence of wave functions between many degrees of freedom. So you have a bunch of waves, right? So say you have a wave from one electron, you have another electron. So a classical system would be made up of many large number of electrons, right? So you have a wave from one electron, then you have from another one, and when you combine all of these waves together, what happens is they lose their wavy or fuzziness, right? So they lose their fuzziness or the wavy nature, and therefore system becomes classical, right? So because you don't have any fuzziness in the system, then you can solve it using classical mechanics, right? So again, if you take a bunch of electrons and you carefully condition them so their wave form are in phase with each other, and so once you do that, you can get macroscopic chunk of stuff, which is why I said you can use classical mechanics to solve for that system. So there you can see that the wave function of a big thing is actually made up of identical wave functions, so therefore they do not interfere with each other. And what this thing is actually called, there is actually a name for it, and it's called a Bose-Einstein condensate, right? Okay, so now let's talk about a nicer idea of making this correspondence between quantum mechanics and Newtonian mechanics, and that nice idea is of the path integral. So there is an interpretation of quantum mechanics that is it is developed using the path integral approach, which was of Feynman. And in path integral, what you do is you calculate probabilities using a weight factor, right? And so what that weight factor is, let's actually skip that diagram and now note that I'm talking about quantum mechanics framework right now. Well, and I'm telling you about path integral, right? So let me write it down. Okay. So the weight factor that I just mentioned is e to the power iota over h bar times the action, that is S. So S is an action, and it is the time derivative of the Lagrangian, and it is actually action is just a way of defining a physical theory, right? So from this weight factor, what it is immediate to see is that for S much larger than h bar, you tend to get phase cancellation, right? And so when S is much smaller, or actually if S is smaller than or equal to h bar, right, then you use quantum mechanics. So you use quantum mechanics, and I think this is much more nicer idea because it directly tells you when do you have to use quantum mechanics and when you can get away with using Newtonian mechanics, right? Okay, well, now we have talked about, if we go back here, we have talked about Newtonian mechanics, we have talked about special relativity, we have talked about quantum mechanics. So let me actually write down this correspondence relation that connects quantum mechanics to Newtonian mechanics, or by using this you can get away with Newtonian mechanics, is S is much greater than h bar, right? Okay, so now what we can do is, why not combine quantum mechanics and special relativity, right? So what we are doing is we are going both small and very fast, right? So we are combining these two and we are getting a framework out of that. Because of course we have to do that, because when we talk about small particles or electrons or protons and so on, what we do is we have to, you might have heard of particle accelerators, the Large Hadron Collider at CERN. What we do there is we take these particles and we collide them at very, very, very fast speed. So that is relativistic speeds. And so of course then we need a framework for doing physics in that kind of a situation. Well, for that we also have, I'm going to actually start from here now. We have a framework, and that framework is called QFT. Now what QFT stands for is quantum field theory. So the name itself gives you that QFT is a framework of fields, right? So we only talk about fields over here. There is no such thing as particles. We are only talking about fields, right? However, there is actually a problem, right? When you try to merge quantum mechanics and special relativity, when you try to get them married to each other in a way, we run into a problem. What that problem is, well, when you talk about quantum mechanics, what is the most important thing that you have to do in quantum mechanics? You have to normalize the damn wave function. Because why do we have to do that? Because of course we are describing something that exists. So if you have an electron and you take an integral from negative infinity to positive infinity, the electron has to be somewhere, right? So in quantum mechanics we have to normalize the wave function. That is because the electron exists. However, in special relativity, and here comes the interesting part, electrons are not forever, you can say. In special relativity, electrons can disappear, right? So when they collide with each other, the particles can disappear and they can also be created. So one of the examples could be when two photons interact, there is a creation of an electron and an anti-electron that is called a positron, and then they quickly annihilate each other and they make another photon, right? So, or another example, or actually just let me write this example for you or draw it for you. So you have an electron and a positron, right? And when they collide with each other, or when they scatter, what you get is you get a photon and you get a photon, right? But again, as we said in quantum mechanics, what happens is that we say that the things exist and they have to remain in existence, and then only we can compute that integral, right? But again, in SR, things can just pop in and out. And so for this kind of a problem, there is an elegant way of combining the two, which is through this quantum field theory, QFT. And in QFT, what you say is that everything is fields. And in here, what we do is particle physics, and QFT is actually the successful marriage of quantum mechanics and special relativity. Right. Now, I'm going to go so far and say that all our frameworks have been covered in this video so far. Right. But now you will notice something, that actually there is a very important idea in physics that we have not included in this video so far, or say we have not said that that is a framework. And some of you might already know about it, some of you might not. Well, that is, of course, the general relativity. So we talked about special relativity, we talked about Newtonian mechanics, we talked about quantum mechanics, we went so far to talk about quantum field theory, but general relativity does not fall into this. Why is that? Well, because general relativity is not, and I repeat, it is not a framework for doing physics. General relativity, or I should say general theory of relativity, it is a theory. Unlike all of these, general relativity is a theory, right? And so therefore it does not fix into this scheme. Now, before I go further, let me say this. Many people think that general relativity is a generalization of special relativity. And well, those are only the people who do not really know about physics or general relativity, because it's not. General relativity is not the generalization of special relativity. Special relativity is actually a result or a solution of general relativity, but general relativity is not the generalization of special relativity. And so general relativity therefore is not a framework, it is a theory. And what is it a theory of? It is a theory of gravitational interaction, right? So when Einstein himself was doing general relativity, or was figuring it out, he was doing it from the Newtonian's idea of gravity, from the Newtonian gravity, and therefore GR is a generalization of Newtonian gravity, right? It is not a generalization of special relativity. And this is a very important point. It is a generalization of Newtonian gravity. And it is required, I should have written down general relativity over here because I was talking about it, but let's ignore that I completely missed doing that, right? Okay, general theory of relativity. Well, I wouldn't actually blame you all for thinking that it's the generalization of special relativity because the name is kind of misleading. But again, now what I was telling you is that it is the generalization of Newtonian gravity, and it is required when this ratio m over r is greater than or equal to c squared over g, where again m is the mass, r is the radius, c is the speed of light, and g is the universal gravitational constant, right? Now you might be thinking, how is then GR related to SR? That is, how is general relativity related to special relativity, right? Well, as I have already mentioned this earlier, SR is just one particular solution of general relativity. That is, when you have a flat space-time, a very boring one, with no gravity at all. And here I would also like to point out, some people think that in special relativity we cannot talk about accelerated frames, right? Well, that's not true. We can talk about accelerated frames in special relativity. So there is no such thing as you have to go to general relativity to talk about accelerations as well. You can do that in special relativity. General relativity is just a generalization of Newtonian's gravity. That's it, right? Now, what we can do is we can paraphrase GR by an analogy, which is with another theory that you probably know well now because I have made videos on it, and that is of the electrodynamics, right? So, well, what do we have in electrodynamics? I'm going to write first over here. We're talking about electrodynamics. Before I go further and make the same mistake as I did with general relativity, I talked about it. and almost at the end of it I gave it a title of General Theory of Relativity. I wrote it down here. Right, so we're going to make this analogy with electrodynamics of what? Of GR. We are going to make an analogy of GR with electrodynamics. And that's we can do that because even in electrodynamics we have a geometry of electromagnetism, right? Okay, so we have a set of equations in electrodynamics. Those are actually pretty famous, and they are that you have gradient of E is equal to rho over epsilon naught, that you have curl of B, and all of these again have vector signs on it, right? We have curl of B as mu naught J. I don't know why I drew that vector sign on J while I did not do it on others, so I'm just going to draw this vector sign on all of these quantities. Right, so we have mu naught J plus mu naught epsilon naught, and we have the time derivative, which I'll write it as this, of electric field E, right? And then the other two equations are curl of E is equal to negative time derivative, partial time derivative of the magnetic field B. And finally we have the divergence of B, which is 0, right? Well, this set of four equations, these are called the Maxwell's equations, right? Now we can go further and we can say that these two equations, they are actually the equations of motion for E and M, right? Electricity and magnetism. And if you don't know about this, you can go and watch my videos on relativistic electrodynamics, and there are a bunch of other videos that I made on electrodynamics. And over there, we actually derive these equations, right? So these are called the field equations. Field equations. And they are equations of motion. Of what? Of electromagnetism. Right? I cannot write it over there. Let me just write it over here. Right? So these are the equation of motion for electromagnetism. Well, then what are the other two equations? These two equations. Well, these are actually called the Bianchi identity, and you learn about these in General Relativity, right? And what are they actually? Let me actually write it down over here. Bianchi. I don't know if I pronounced that right, but well, that's why I wrote it for you, right? Okay, so these are the conditions that are posed on what? On the electromagnetic geometry. And now this kind of sounds weird and all. Electromagnetic geometry, what is that? Well, you learn about that in General Relativity, right? So there is a geometry of electromagnetism as well. Okay, now altogether, again, these four equations, they give us the Maxwell's equations. Now the question is that even I kind of feel bad about not telling you about this in my videos on electrodynamics, but the question is, what do these Maxwell's equations tell us? So you talk about these equations, you deal with them very rigorously as well, but what do they tell you? Well, they tell you that how the sources that are, again, rho and J, that is the charge density and current density, right? So this one, rho and J, these are the sources. So how do these sources creates the fields, that is electromagnetic field and I'm sorry, that is the electric field and magnetic field, right? So how do these sources create these two fields, right? With some topological constraints. I don't know if I pronounced topological correctly, but you get the point, right? I'm just going to write it down. Topological, right? Okay, again, Maxwell's equations tell you how the sources rho j create the electromagnetic fields with some topological constraints, right? Okay. Well, this is actually just half of electromagnetism that I have written down over here. There is another half of electromagnetism. And what that other half of electromagnetism is that how a particle that is placed inside a field is going to react, right? And what is that? That essentially is inside this Lorentz force law, right? So Lorentz force law. And of course, if you're watching this video, you might already know about this. It's F of force of electromagnetism is Q, that is the charge, times electric field plus V cross B, where again V is the velocity of the particle, B is the magnetic field. This equation also tells you something. And what is that? That is that how does this force or what is the force on the particles? And then the question is that how this force affects the behavior of particles. So this force arises due to this electric and magnetic field, and how does this force then change the behavior of the particle, right? That's the question, and that's the other half of electromagnetism, right? Well, what we can do is we have Newton's second law for this, that is F equals ma, right? And what you can do then is you can equate these two, and then you can solve for the question that how does this force affects the behavior of particles, that is the dynamics of a particle, right, due to this force. Let me give you an example actually, right? Say, for example, you have a hydrogen atom problem, and there you have a proton, and for that, what you do is you compute the electromagnetic field for that proton, right? And what you do is then you forget about the proton itself, except for the field that you just calculated, the field that arose due to the proton, right? And then you completely forget that there is a proton or whatever. You just keep in mind that there is this field, and then you put an electron in that field, and then you see or solve the equations to see how does that electron act in this field that was created due to proton, right? So this is something that we do a lot in physics. We use these big things, let me call them big things, to create backgrounds for us. In our case, we used the proton, that was the big thing, compared to an electron, of course. And we created this background by solving for it the equation that would give us the electromagnetic field that this proton produced, right? And then we use small things like test particles. In this example that I just gave you of the hydrogen atom, the test particle was an electron. And so we use these test particles in this presence of the background, which again, the background is this field due to proton. And then we see what do they do, right? We look at them and see the funny things that they're going to do, the particles that are going to do in this field. Okay, well, we talked a lot about electrodynamics, even though this is not a video on electrodynamics. Again, it is a video on the frameworks for doing physics. So let's actually get back to GR, general relativity. General relativity kind of exactly mirrors this what I just told you about electrodynamics, right? So what do we have in general relativity? In general relativity, the analogous to Maxwell's equations, we have Einstein's equation, right? Or you can say Einstein's equations, because the Einstein equation itself has a lot of components, and well, you can write them in several equations and you get many equations. So it's up to you. You can say Einstein equation or Einstein's equations. Okay, so again, in general relativity, Einstein's equation, let me write it down over here. In general relativity, Einstein's equations, what do they tell you, right? Right. So Einstein's equations in general relativity, they tell you how sources are going to create fields or the curvature in space-time, right? So the curvature of space-time plays a very role of the gravitational field. So you had this gravitational field in Newtonian mechanics, and in general relativity you don't have this gravitational field, but we do have a field in general relativity, and that is actually a very realistic field. It's called the metric field, right? But we don't have this gravitational field as such you had in Newtonian mechanics, right? Well, again, there should be another half to general relativity as well, and that other half is described by an equation that is called the geodesic equation, right? The geodesic equation. And again, analogous to electrodynamics, what this equation tells you is how a test particle responds to that curvature, right? And well, when we get to geodesic equation, that is a very beautiful part, because that is where you get this Big Bang and black holes and all that other stuff. But when you get those solutions, right, you have to have a complete faith in the result that you get from the Einstein's equation, that is this. So I would recommend when you teach general relativity, you should always start with the Einstein's equations and then go to the geodesic equation, right? Because you have to have a firm belief and faith in what this Einstein equations are going to tell you. And then when you get these solutions that are very weird and bizarre, that gives you black holes and the Big Bang and so on, so you can question those, but you cannot question those if you know exactly that the Einstein's equation that you solved is giving you correct results, right? So if you understand that, then you can enjoy doing or solving the geodesic equation. Again, we kind of shifted very off topic. The main thing was actually to tell you about the frameworks for doing physics, right? And then what I did is, of course, told you that general relativity is not a framework, but it's a theory and the generalization of Newtonian's gravity. Again, it is not the generalization of special relativity. And so I had to tell you then, why was that so, right? And therefore, then I had to discuss general relativity. I went into talking about electrodynamics and then making this analogous relation between general relativity and electrodynamics and so on. But the main idea again was to tell you about the frameworks in which one can sit and do physics. And so here I have ended my discussion, or a lecture you might say, and I hope that this gives you a better insight to physics.